And this is the introduction to the course of Dynamics ME213. The course of Dynamics is an extension of the course Statics, which the students studied in the previous class. First, there is introduction of the subject Mechanics. Mechanics is a branch of physical sciences that is concerned with the state of rest or motion of bodies subjected to the action of forces. So mechanics includes study of the objects which are at rest or in motion. In the subject of statics, the objects or bodies were considered to be at rest. In dynamics, the study of the motion of objects or bodies will be studied, and the forces which are responsible for creating the motion will also be discussed. The subject of dynamics has two main portions. One is kinematics and second one is kinetics. The kinematics deals only with the geometrical aspects of the motion. The motion is described only in terms of parameters, quantities such as velocity, acceleration, displacement. The forces which are creating the motion are not considered in the topic of kinematics. On the other hand, the kinetics is the study which includes the forces. It calculates the forces or moments which are creating the motion of the object. So kinematics is the branch of dynamics which describes the motion of the bodies without reference to the forces which are creating the motion. The subject of kinematics or topic of kinematics has several applications. Two applications are listed. They are used, the knowledge is used in the design of machine components and elements such as cams, gears, and other machine elements, and the study is also applied in the motions and flight trajectories of the aircraft, rockets, and other airplanes. In the topic of kinematics as well as in kinetics, there are two subtopics. One is only the study of the particle, and the second one is the study of the rigid body. When we consider the particles, we assume that the dimensions of the object have negligible effect on the analysis. The basic definition of particle is that it is the object which has negligible size or shape. And when we are assuming any object as a particle, we assume that there is no effect, there is no consequence on the analysis of the motion. So particle is used in a broader sense. Even a vehicle, airplane can be considered as a particle. So if you are not interested in the dimensions or the various locations on the object, the motion of the various locations of the object, then we can assume a large size object as a particle. So in the particle, when we are considering the particle, the different material points on any object are not distinguished. So as I mentioned, the rockets, airplanes, vehicles can be assumed as particle as long as the motion is characterized by the motion of the mass center. So main assumption is that the dimensions is not important in the analysis, and we are neglecting any rotation of the body. We can also assume the particle We can also assume object as a particle if the physical dimensions are small when compared to the radius of curvature of the part. For example, airplane, if you are assuming if you are calculating its if you are analyzing the trajectory, for example an airplane, if you are analyzing its trajectory, the physical dimensions of the airplane are much small when compared to the radius of curvature, or when compared to the distance it travels during its entire journey. The main elements of kinematics are velocity, position and acceleration vector. When we define velocity, position, acceleration, we do not require any coordinate system. But when we are studying the kinematics of a particle, when we are determining velocity, position or acceleration of a particle, then we need a coordinate system. There are various types of motion. We consider a simplest type of motion in the first instance. The simplest motion is the motion which is in a straight line, which is termed as rectilinear kinematics. So for the study of the kinematics, we first consider the position. For the straight line motion, a single coordinate axis is sufficient. So we consider a single coordinate axis, which is S, and on the axis we mark a point O, which is the origin. For the various quantities, we need this coordinate system and we need the origin. Suppose the particle is located at a certain line on the coordinate axis. The position is suppose P. If we want to determine the position vector, if we want to draw a vector for the position, then we will draw an arrow from O to location P. This will be the position vector. Then displacement is the change in position. The particle initially is at this location. The particle changes, it moves and it reaches somewhere here. So this delta S will be the displacement. The displacement in this case will be positive if the particle is moving away from the origin. If the particle is moving towards the origin, then delta S or displacement will be negative. Second quantity is average velocity. The displacement divided by the time spent for the displacement will give the average velocity. Then the next quantity is instantaneous velocity. If the amount of time is close to 0, it approaches 0 or tends to 0, then in that case the velocity will be the instantaneous velocity. So instantaneous velocity is also a vector and it is written as ds over dt. So here dt is always positive, ds and v can be negative depending on the motion of the particle. If the particle is moving towards right, the velocity will be positive. The next quantity is average speed. Average speed is a scalar quantity. It is calculated from the entire path which is traveled by the particle. Suppose the particle initially was here, it moves towards right, then after some distance it moves towards left. So for the calculation of the average speed, we will consider the entire path, entire distance which is traveled by the particle. On the other hand, if we are calculating the average velocity, then we will consider only this distance, which is delta s, and here the average velocity will be negative. But for the average speed, we will consider the entire path which is traveled by the particle. Then next is average acceleration. It is determined from the average velocity or change in velocity. It is calculated from the change in velocity. Delta V represents the difference in the velocity during the time interval. So initially the velocity is v, and after some time it is v dash. So the two velocities will give the difference delta v, and delta v divided by delta t will give the average acceleration. Again, if the time interval is small, it approaches 0, then in that case we will have instantaneous acceleration, which will be dv over dt. Since v is equal to ds over dt, the acceleration can be written as the second differential of the displacement. We can see two cases. In first case, the velocity increases. The increase in velocity is shown with the help of the size of velocity vector. So velocity here is increasing. When velocity is increasing, the acceleration is positive, and the acceleration is shown in the positive direction. When the velocity is decreasing, as in the second case, the size of the vector, you can see it is decreasing. If the velocity is decreasing, the acceleration will be negative, and the direction of the acceleration will be towards left. Even though the particle is moving in the positive direction, the direction of acceleration is in the opposite direction. So this will be considered as the acceleration. From the two relations, v equal to ds over dt and a is equal to dv over dt, we can eliminate dt from the two equations, and we will get a relation between acceleration, velocity and displacement. So now we have three relations. V equal to ds over dt, and then a equal to dv over dt, and this is the third relation. If we assume acceleration to be constant, acceleration is not changing with respect to time, then we can have simple relations which the students have studied in their metric or intermediate course. So this is the same relation, but this relation is only valid when the acceleration is constant. Now the previous analysis, which is through the three differential relations, and for the special case of the acceleration to be constant, we have these three simple relations. Sometimes the motion is irregular. Irregular means that we do not have a single relation, for example for the velocity or acceleration for the entire motion. Suppose the object is moving and the entire time interval is, for example, 100 seconds. During the 100 seconds, the motion is not continuous. Suppose sometimes the object is stationary, sometimes it is moving with a constant velocity, sometimes it is moving with variable velocity. Then in that case we have to split the entire motion into small steps or finite number of steps, and for the multiple steps we have separate relations. We also study the irregular motion with the help of various curves, the curves between position and time, velocity and time, and acceleration and time. Suppose we have the curve for the position and time, and we are interested in determining the curve for the velocity and time. So suppose we see this curve. This is suppose given. The position is increasing, that is the particle is moving away from the origin, and then position value is decreasing, or the distance from the origin is decreasing. So this is the curve which is given. From the slope of the curve we can determine the velocity and time curve. So here we see that the curve is positive, the slope is positive for the curve between S and T. The curve slope decreases, it further decreases, and then the slope becomes negative. So when the slope is increasing, the velocity is positive. When the slope reduces, the velocity reduces, and finally when the slope is negative, the velocity is negative. So using the slope of S and T, we can plot the graph between velocity and time. In the similar manner, if the acceleration and time graph is given, we can construct the velocity and time. Since acceleration is equal to dv over dt, the slope of velocity and time curve will give the value of acceleration. So we can see in this chart, we can see in this graph that velocity is 0 because the acceleration curve has very less slope. The slope is close to 0 in the beginning. When the slope is very less, or it is close to 0, then acceleration will be 0. With the passage of time, the curve has some slope. It has a positive slope. When the slope is positive, the acceleration increases. Acceleration has a positive value. Then acceleration reduces. The reason is that the slope of the curve is decreasing with the passage of time. Now we consider the opposite case. Suppose the acceleration time curve is given and we want to sketch the velocity and time curve. If you see the formula for calculation of the velocity or the velocity change, we have to integrate, because A is equal to dv over dt. But if you want to find velocity, we have to integrate acceleration and dt. So acceleration multiplied by dt is area under the curve. The area under the curve will show the change in velocity. For this plot, we have to assume the initial velocity, which is v0. That is, we assume that the initial velocity is known. If the initial velocity is known, then we can mark the second point, or we can mark the distance delta v. So delta v is equal to a multiplied by dt. There is a certain value of a at this particular location. Since this element is thin, we ignore the changes of acceleration. So acceleration at this particular point and multiplied by the small value of time. This will give the velocity difference. Suppose acceleration is 2 and delta t is 1. So 2 multiplied by 1 will give 2. So this means velocity increases by 2 meter per second, for example. Similarly, if you want to calculate the velocity change at this value of time, we will consider the acceleration at this point and then we multiply with dt whatever it has the value. The multiplication will give the velocity change at this particular location. Similar is the case for the position time curve. If the velocity time curve is given, we can plot the position time curve. The formula is delta S equal to V multiplied by dt, and here we assume that the initial position is known. Suppose initial position is 5 and here suppose dt is 1 and velocity is 10. So at this particular location we suppose that velocity is 10 and we neglect the change in velocity because the element is very thin. So 10 multiplied by 1 will give 10. So position will change from 5 and then here it will be 50 because there is addition of 10. Now we can have few more cases. Suppose the acceleration and position curve is given. Suppose we do not know the time. We have the acceleration as constant or we have the acceleration in terms of s. So using this data we can find the change in velocity. Acceleration multiplied by ds. Suppose ds is 1 and acceleration is suppose 5. The multiplication will give the change in half v1 square minus v0 square. Again we assume that v0 is given. So when v0 is given we can find v1. So here we will not have directly the change in velocity, rather we will be having change in half v1 square minus v0 square. Now the opposite case is that when velocity and position curve is given and we are interested in getting or knowing the acceleration or plotting the acceleration position curve. Again using the same relation, ADS is equal to VdV, acceleration is V multiplied by dV over ds. So if we see the curve at a particular location, we find dV over ds. Since we have the curve, we can find the slope of the curve at this particular location. Then we multiply with velocity at the same location. We multiply the velocity at the same location at where we are calculating dV over ds. The multiplication will give the value of acceleration at that particular position. Suppose dV over ds is 1 and velocity is 20. So the multiplication will give the value of acceleration at this particular location. So acceleration will become 20 at this value of s. The next topic is general curvilinear motion. Previously we considered the rectilinear kinematics in which the particle was moving in a straight path. Now in this topic the curve path will be considered. To study the curve path motion or curvilinear motion, suppose this is the space curve and this particle is moving along this curve path. To identify the location of the particle on the curve, we mark a point O which is fixed, and from this fixed point we draw a vector. The position vector will be r, and this position vector r will be function of time. The magnitude as well as direction of this vector will change with the passage of time. So position vector is function of time. Suppose this is the initial location of particle. After some time the particle reaches up to here. Initial position vector is r and the final position vector is r dash, and the difference of two vectors is delta r. So delta r will be the displacement. In addition, delta s is also shown. Delta s will be the distance. Since it is a curved path, the length delta s and delta r will be different. Delta r will be less than delta s because it is the displacement. So we use the vector addition. Delta r will be r plus delta r. Sorry, r dash is equal to r plus delta r, and similarly delta r is equal to r dash minus r. So this is the simple vector addition. To obtain velocity is also a vector. To determine average velocity, we will divide delta r with delta t. When the time approaches 0, then the velocity will be the instantaneous velocity. Instantaneous velocity will be dr over dt. The symbol r with bold is basically the vector quantity. In the book, the nomenclature is that if a quantity is written in bold, then mostly it means that it is a vector quantity. If this same quantity is shown in irregular font, then it will be the magnitude or scalar. Now delta r will be tangent to the curve. If we are considering the instantaneous case, then delta r will be tangent to the curve. When delta r is tangent, then velocity will also be tangent to the path. So velocity is always tangent to the curve of the path of the particle. So here we can see that this is velocity. Velocity is always tangent to the curve. The reason is that the displacement is tangent. For a small time, displacement is tangent, so velocity is also tangent to the curve. Then if you want to determine the velocity or magnitude of velocity, then it is speed. For calculation of speed, we can simply take the magnitude delta r, or we can take magnitude delta s. For small time, delta r and delta s both are same. Then velocity magnitude or speed will be simply ds over dt. Then next quantity is acceleration. Acceleration is determined from the change in velocity. Suppose initial velocity is v and at second time instant the velocity is v dash. For the calculation of average velocity, we will determine delta v and then divide with delta t. This will give the average acceleration. Now how we will calculate the value of delta v? Delta v is v dash minus v. From the background of basic physics, we know that for calculation of delta v, we have to join the tails of the velocity. We join the tails of the velocity and the difference will be delta v. So using the vector addition, v plus delta v is equal to v dash. the direction of delta v and acceleration will be same, because acceleration is determined from velocity difference. So direction of acceleration is same as direction of delta v. The direction of velocity and direction of delta v will be different, because this is the direction of velocity, this is direction of velocity at second time. The direction of delta v is different from the direction of velocity, and the direction of velocity difference and acceleration will be same, because acceleration is determined from delta v. The plot for the direction of acceleration or delta v is hodograph. The path of the particle is direction of delta r, and hodograph is the direction, or it is the curve for direction of delta v. The path of the particle is for delta r, that is delta r lies on the path of the particle. Similarly, delta v lies on the hodograph curve. The definition of hodograph: it is the locus of points for the arrowhead of the velocity vector. So hodograph is the locus of the head of the velocity vector. This is the head of the velocity vector at one time, this is the head of the velocity vector at second time, and suppose the third velocity is somewhere here. When we have the common origin, this is the velocity direction. So hodograph, it describes the locus of points for the arrowhead of the velocity vector in the same manner as the path describes the locus of points for the arrowhead of the position vector. So path of the particle is the locus of points for the arrowhead of the position vector, whereas hodograph is the locus of points for the arrowhead of the velocity. Now if we are interested in determining the instantaneous acceleration, then again time will tend to 0, and we will get acceleration vector as dv over dt. Again, this is a vector quantity since it is written in bold, and acceleration can also be written in terms of second derivative of the position vector. So acceleration is tangent to hodograph, velocity is tangent to the path of the particle, acceleration is tangent to the hodograph. Acceleration is not tangent to the path of the particle, acceleration is tangent to hodograph, velocity is tangent to path. Acceleration is not tangent to the path of the particle.